Hey there, welcome to Geometry Lesson 5. And I'm going to start off this lesson by pointing out that I do not like the way that this lesson is. If you look at the title, it's More Theorems About Lines and Planes. It's a continuation of the last lesson. And if you think back to the last lesson we just learned a ton of postulates and theorems. And it was a long list of things that was way too long for you to actually memorize and make use of. And this lesson is going to give you even more theorems and one more postulate. It's just way too long a list of things for you to memorize and make use of. Also, compared to the last lesson, this one's a lot more complicated. In the last lesson, at least you probably felt as we went along, like the postulates and theorems we were learning were pretty intuitive. They made sense. I didn't have to explain them a whole lot. I could show you a figure and show you what was happening, and you could just, your brain can think through it and say, yeah, that makes sense. These ones are a little more complicated. You can still do it. It's just that we're holding more figures in your brain at the same time, and it's hard to think through all of them at the same time. All right, now, let me ease your mind a little bit. You're not meant to memorize all of these theorems and postulates. What these two chapters are meant to be is a reference that you can go back to and pull theorems and postulates later on as you need them for proving concepts in geometry. So you should remember chapters 4 and 5 contain a lot of the postulates and theorems you need. And actually, even better, there's a section in the back of your book that lists all of the theorems and postulates one after the other. And you can pull from any of those theorems and postulates later to prove things when we learn about geometric proofs. Okay, so that's just a little introduction. We are going to be learning several more theorems and one more postulate today. I'm going to start though by just sort of reminding you about perpendicular and parallel lines. Here I have a square, and I've indicated on this square that we have some lines that are parallel. The top line segment WZ is parallel to the bottom line segment XY. Now I could write out the statement like we did last time. WZ is parallel to, with the double lines, XY. Another way to show that two lines are parallel is to put little arrows on them. I put a single arrow on WZ and XY, and since it's the same kind of arrow on WZ and XY, it shows that those two are parallel. On XW and YZ, notice I use a double arrow. The double arrows are different from the single arrow. So it shows that something with a single arrow is not necessarily parallel to something with a double arrow. In this case, it's obviously not parallel. But anything with a double arrow is parallel to anything else with a double arrow. So I could show from the figure that XW is parallel to YZ just from the way that I've drawn this figure. Okay, then perpendicular lines are shown with a right angle. Notice that WX and WZ have that little right angle sign between them, a little square in the corner. That shows that that's a 90-degree angle and indicates that these are perpendicular lines. Now, could I show that the angle XYZ is also a right angle in this figure? I could, but I need some rule that shows me that. I need some way to prove that. And I need some postulates and theorems that indicate that that's the case. Otherwise, I'd have to come up with some argument to prove that XYZ is perpendicular. All right, let's see if any of our theorems do that for us as we move along. And I'm going to be trying to demonstrate all of these theorems using some figures that I have drawn for you. Please pay attention to the figures as I explain the theorems, because that's really going to help you to understand what's happening here, understand what the theorems mean. And like I said, these theorems are a little more complicated than the previous ones. Let's take a look at theorem 5.1. And again, this is chapter 5, so we're looking, the theorems are going to be numbered 5 dash something. Okay, here's 5.1. If two parallel planes are cut by a third plane, now we're looking at that cube, okay? So we see we have two parallel planes on either side of the cube. We'll look at planes ABH, find ABH, and CDG as our two parallel planes. And we're going to cut those by a third plane. Let's look at plane ABC, the front of the cube. If two parallel planes are cut by a third plane, then the lines of intersection are parallel. Okay, let's think about this one for a second. We have two parallel planes cut by a third plane. Anytime planes intersect, they intersect at lines. Do you remember that? Anytime two planes intersect, they intersect at lines. So I'm looking at that cube, and I'm looking at those two sides, ABH and DCG. And I see that where they intersect with the front of the cube, there's actually a line of intersection between those planes. And what this is saying is that those lines are parallel. So AB is going to be parallel to DC because ABH and DCG were both parallel planes, and the plane ABC intersected both of them. Now, I just want you to imagine, what if ABC wasn't like perpendicular? This wasn't a cube, and ABC kind of like intersected at an angle, okay? Now, it doesn't matter if ABC intersects at some weird angle, whether it's like really oblique or a really shallow angle. It doesn't matter. No matter what, the intersection of ABC with those two parallel planes on the side is always going to be parallel lines. One line where it crosses plane ABH and one line where it crosses plane DCG. Okay, so I could really easily demonstrate it on a cube. Important to note that it works on non-cubic figures as well. All right, we'll just file that one away. Let's take a look at the next theorem. If two lines in a plane are perpendicular to the same line, then they are parallel to each other. Two lines in a plane are perpendicular to the same line, then they are parallel to each other. Let's go back to our cube once again. AB and CD are both perpendicular to AD, okay? So look at AD across the top. AB and DC are both perpendicular to that top line. Okay, if they're perpendicular to the same line, that's a way of indicating that they're parallel to each other. If they make 90-degree angles with the same line, that's a product of the line AD being straight, okay? All lines are defined as being straight. So if you have two other lines that are both perpendicular to that straight line, then they have to be moving in the same direction. That the perpendicular means that they're moving in the same direction compared to each other and exactly at a right angle to that first line. So that means that those two lines are going to be parallel to each other. Now again, see how these are taking a little bit more thinking to make sense of, but you can definitely make sense of them, especially when looking at figures. In a plane, if a line is perpendicular to one of two parallel lines, then it's perpendicular to the other one. I'm actually going to bring out a third figure that might help us with this. So here I have three lines. Two of these lines are parallel. You see my little parallel markers here. And one of these lines that cuts across is perpendicular. So these are all coplanar because they all intersect each other. And two of these are parallel. Parallel lines are also coplanar. In a plane, if a line is perpendicular to one of two lines, so we're going to say line R, notice, is perpendicular to line P. And one of two parallel lines, P and Q are parallel lines, then I can also say that R is perpendicular to the other parallel line. Okay, it has to be because it's moving in a direction compared to P where it crosses at a right angle. Since Q is moving in the same direction as P is, then R must also be perpendicular to Q. See what it means? Okay, so again, these are a little bit more complicated that you have to hold more figures in mind at the same time. Usually we're dealing with three figures at a time, but your brain can make sense of them with some slow, careful thought process. If two lines are perpendicular, then they form congruent adjacent angles. And this is another thing I hate when textbooks do. We don't define adjacent angles until lesson 6. But yet, here we are using the words adjacent angles. Now, part of the reason we do that in this book is because this chapter is meant to be a go back and look at it reference chapter. So it doesn't really matter that we're talking about adjacent angles yet because later on is when we're actually going to be using what we say. But let me explain. Adjacent angles are two angles that are right next to each other. They are touching each other, and in fact, they are sharing a side. Okay, two angles that share a side. So what we're saying here is that if let's go back up maybe to, no, let's just do this angle, this right angle that's marked here between P and R on the top side forms an adjacent angle with this angle on the bottom side of the intersection of P and R. But because this one's a right angle, this one also has to be a right angle. Part of that is realizing that a straight angle is 180 degrees. Okay, a straight angle is 180 degrees. And if 90 of those degrees are taken up by one angle, there's only 90 degrees left, exactly 90 degrees left to be taken up by the other angle. So this other angle has to be 90 degrees too. That one makes more intuitive sense. You're only holding a couple figures in mind at the same time. So does that make sense? 90-degree angle, this has to be a 90-degree angle. Hey, if this is a 90-degree angle, this has to be a 90-degree angle. And if this is a 90-degree angle here, this one over here has to be a 90-degree angle. So where two lines cross, if one angle is perpendicular, all of the angles are perpendicular. But that's not one of our theorems. That's just something that's easy to prove from Theorem 5.4. If two lines form congruent adjacent angles, then they are perpendicular. Whoa, let's think about that one. Let's go to P and R again. If I have two angles that are next to each other that are the same size, what size would that be? So I have two lines crossing each other. What are the sizes of these two angles? Well, if they're congruent, that means I'm going to have to, that means that P is really an angle bisector for a straight angle, okay? This angle is 180 degrees. For these angles to be congruent, they each have to be 90 degrees for them to be the same size and add up to 180. So does it make sense that they would be right angles? And any angle that's a right angle shows that the lines that make that angle are perpendicular. That's what we have going on in Theorem 5.5. And then Theorem 5.6 is also pretty simple. All right angles are congruent. What are congruent angles? Are angles with the same measure, right? And right angles have a measure of 90 degrees. So because right angles have a measure of 90 degrees, and they all have the same measure, they all have to be congruent.